give a brief overview of who we are and our background. Then we will look into typical challenges that extrusion industry face and how easy it is to analyze them and fix using Click2Extrude. And finally, we will open up the line for discussion. Altair is a 30-year-old company that has extremely deep roots in engineering simulation. Our philosophy is to radically change the way organizations design products and make decisions. We have over 2,300 engineers in 23 countries and over 45 offices. And SolidThinking is a subsidiary of Altair. Worldwide customers, we have over 5,000 customers worldwide using all our products in different verticals. And among them, we have 100 plus companies who are using Click2Extrude today. At a high level, what is Click2Extrude? It is polymer extrusion simulation software that is fast, easy, accurate, and affordable, which allows users to enhance and optimize their extrusion process for massively improving the quality and productivity of the extrusions. What are the challenges faced in extrusion industry? If you look into the extrusion life cycle, it starts from designing the desired shape. Then based on the shape, we design the die for it, and the die gets fabricated. After the fabrication, it goes to die trial, and finally it goes to production, and the part is shipped to customer. If you look at the traditional process, the cost to fix problem gets exponential at later stages of the production. Typically, if you look at number of iterative corrections at each stages, as shown here, most of the iteration occurs traditionally during the die trial, which is after fabrication stage, and in production stage. Using Click2Extrude, the entire process can be radically shifted upfront during the die design stage with virtual simulation before any die is fabricated. This drastically reduces cost while widely improving the quality. It very well goes with our philosophy of simulation-driven design and manufacturing. Here I have listed typical extrusion defects that we encounter in polymer extrusion, like profile distortion of the polymer is coming out of the die swell of polymer getting swelled as the polymer is coming out of the die, and issues in co-extrusion, and issues in co-extrusions with metal insert, and clamshelling or tool deflection or stress analysis. Before I go into details of each of these defects, I will show a quick demo of Click2Extrude, how to set up the model. So here is the new interface for Click2Extrude, and over the period of 20 years, we made the process, simulation process, very easy to use, and the entire process can be done in very few mouse clicks, and no prior knowledge of C is required. So I'll bring in the die geometry. So the simulation starts with the 3D die geometry of the tool assembly, what we are going to use to extrude the desired shape. So in this model, I have 5 plates that is being used to extrude this complex thin profile section. And as soon as the die is brought it into Click2Extrude, the next step is to orient the die or position the die. So here the die is already oriented in correct direction. I have to position it to global origin. Next is to extract the flow volume. Flow volume is nothing but the region where polymer is entering and touching all die surfaces and coming out of the die. So with one simple mouse click, we can extract the entire flow volume that is made by the die assembly. And as it is extracting the flow volume, it will also extract if you have pinholes or any holes that is meant for cooling or heating the die to maintain the temperature. So we only keep what is where the polymer is flowing and will discard all unnecessary solids. Okay. We can simply press delete button. Next is to here we are only extruding single polymer. If you have two polymers, you have two inlets coming in. So next step is to select polymer that is we are going to use to extrude this profile. So here I'm going to go with PVC generic. Next is cut line. Cut line is required when you are extruding two or more polymers. So here, since I'm extruding single polymer, I'm going to skip that step. Next step is to organize extracted solid into layers. So since I have everything belong to one polymer, so they will go to layer 1. And if you have a co-extrusion die, set of one solid which belong to one polymer will go to layer 1, and set of another solid belong to second polymer will go to layer 2. So once all solids are organized into layers, next step is to create profile solid, and this profile solid is used for determining how the part is going to deform or twist as it is coming out of the die. So here I'm going to take the default profile length. Now my whole model setup is complete. So here is what I did. I imported the die geometry, extracted the flow volume, selected material that I'm going to use for extrusion, then cut the land if it is required for, which is required for co-extrusion, and then finally organize and create profile solid. Now next step is to define what are the process conditions, like what speed and where the polymer is coming in and where it is exiting. Okay. So we specify, so it's coming at 250 degrees Fahrenheit and let's say 10 inches per minute, and it is exiting from here. And the die could be very complex. So here you can also specify what is puller speed. If there is a puller which is pulling out the profile, you can define that too. So now the model setup is done. We also have a few more options which are optional, not required for all the dies. One is for defining wall conditions. So if you have some special temperature control on die, so you can define those special conditions on the die wall. Or if you have symmetric die and you want to do a partial simulation to get the solution quicker, so you can define a symmetric boundary condition also. And if you have insert in the profile, you can define insert too. So here I do not have all those options, so I'm going to skip that. So the whole setup is done. Next is I will save the model and submit for analysis. Before I do, I delete all the tool geometry I don't need. So this covers how to set up the model. I can close the status bar, and anytime I can go to the run status and it will bring back the status, what is happening with this model. So I covered how to set up the model. We also have some geometry tools. If the geometry has the die geometry, what you are importing, that has some issues, we also have some tools to patch the geometry or make some modification into the geometry to correct it and make it workable for performing the simulation. So now I will go back, as the simulation is running, I'll go back to my presentation and come back to post reviewing the results at end of my presentation. So first, let's discuss about the profile distortion and how to rectify using Click2Extrude. First and foremost, an extruder or a die maker would like to know is if the die is balanced, if the die is going to produce the profile as per the requirement, or it will adhere to all tolerance and dimension integrity. The typical reasons why the die tryouts will fail is you have a very complex shape that you are extruding where the thicknesses are changing a lot, and you are extruding newer polymer, or you are adding some new additives or coloring agent to the polymer that could also drastically change the flow behavior of a known polymer, or you are extruding dissimilar polymers like in co-extrusion. So Click2Extrude helps in predicting how the distortion upfront accurately and quickly. So based on how the part is coming out of the die, we can make the adjustment in the feeder or the feed section or the transition zone to make the flow better and make the deformation and make the uniformity in the velocity. So next I'm going to show how the same die what I was set up just now. So here I'm showing how the part is deforming and what are the velocity variations. So if you see in this image here, the right hand side is thick section, very thick section compared to other regions in the profile, and that is why the right section is coming out faster, and also the feed before that is bigger compared to the other regions, and that is making it to come out faster compared to other regions. So here if you look at the distortion and speed variation, it shows the speed variation, and the rightmost is coming out very fast, and the left one is little bit not that very fast. And as you can see that edges shows the desired shape, but it is not conforming. So we can go back and make adjustment into the die or the process condition and try to minimize this distortion into the profile. Here I'm showing a die with multiple profiles coming out. So the aim is to get profile uniform in all the outs. It may be you have designed the die geometrically symmetric, but due to the temperature gradient, the center could come faster compared to the outer one, or vice versa. So with Click2Extrude, we can understand like if multiple profiles are coming out, how each profile is coming out, are they coming out uniformly? And here we can see, since there is a large variation in thickness, the thick section is coming out faster, and that is why it is twisting in the one direction. Next, we'll discuss about die swirl. Polymer is a viscoelastic material, and it has normal stress effect and memory effect, which causes the extruded to swell after it leaves. So die swell is an instance where polymer stream is compressed by entrance in a die, and it's followed by partial recovery or a swell back to the former shape and volume of polymer after it exits the die. This behavior can be reduced, or it depends on the polymer that you are extruding, process conditions, and die design. Mostly it can be reduced by making the land longer or increasing the polymer melt temperature, but all this leads to overheating of polymer too. So we have to control the land length, the temperature, and it's a highly nonlinear problem. So Click2Extrude helps in predicting what die swell will come and make the modification in process condition or the die design itself, and predict what the die swell will come and how to minimize the effect. So overall, it affects the quality of part and the throughput. Next, I'm showing one case study where extruding a rod coming out of the die. So here it shows how, as soon as the profile is coming out, how the profile is expanding as it comes out of the die, and slowly it's shrinking because of the pulling effect. So that's what you see in the graph here. So it is expanding and then shrinking it down. In next slide, I'm showing the differences of differences in die swell for 4 different polymers. They have different flow behavior properties, and the one on the bottom right shows almost 3 times the die swell compared to the top left image. Next, I'm going to discuss about co-extrusion, the issues that we come across in co-extrusion. Determination and control of interface between, so it's very important to determine how the polymer is coming together in the land region and forming the interface as it's coming out. And the challenge also we face is the viscous encapsulation, where the interface between 2 polymers gets shifted from its desired location, and you don't get the dimensional integrity into the extruded part. The factor affecting the co-extrusions are the differences in polymer viscosity, the die design itself, like we use same adapter plate and transition plate for most of the different shapes, and that could affect how the polymer is going to come out. So it depends largely on die design, and also on the process condition that we are using, like what speed the polymer is coming in, each polymer what we are pushing, and what is the temperature and how the temperature is changing during the flow. So Click2Extrude helps in determining what is the cause of issue and how to rectify them. To show a viscous encapsulation effect, so here I'm showing one simple example where 2 polymers are coming and they're not touching in first place, and they are joining at this region and they're coming out. If this polymer, if they are of same viscosity, and if I pump the blue one with 10 millimeter per second and the yellow one with 20 millimeter per second, and because of that difference in velocity, this interface between these will shift, to upward direction. And that's what we are seeing here. So this yellow is getting the deformed shape become red. So it is taking the area or shifting the interface between the two polymers, and that's how it's coming out. The same could be visualized or seen when there is if you are extruding two different polymers with different viscosity, even though they are extruded in same temperature or velocity. So next, I'm showing one automotive seal problem where two polymers are being extruded. So the blue one is a high density polymer, and the light orange or pink is a low density polymer. And here the aim was to understand how the interface between these two polymers is adhered to, is within the tolerance or not. So here we can see as the polymer is flowing through the die and coming out of the die. So because of the viscous heating, the temperature will rise. So here we can see how much the temperature rise in the die as the material is flowing through. And this will help us understand if the temperature rise is within the limit or temperature rise is uniform across at the die exit. If there is high variation in temperature, like what we are seeing here, the bottom rib is coming a little bit colder. So we will see some defects because of variations in the temperature. Next, I'm showing how the interface, so this is the desired shape, and how the interface is getting shifted because of the differences in the viscosity of these two polymers. This is another example of co-extrusion of a very thin profile. So two polymers are coming in, one is coming from top and one is coming from center. And we can analyze how the pressure is dropping as the polymer is flowing through the die cavities, and as the material is flowing through, how is the temperature rising because of shear heating effect near on the die wall and between the shearing between them. And we can also see how the actual flow is happening inside the die. Next, I'm going to discuss about the issues that we face in co-extrusion with metal insert. A metal insert is used in many profiles to reinforce the extruded part that is coming out of the die for the end use. So mostly we will see these parts in automotive or some similar application. So the main reason of adding insert is to reinforce. So the problem what we see in such dies are centering of this metal insert. So because of the viscosity of the profile that is getting pushed, that can shift or push the metal insert in one direction, and that could change the centering of the metal insert. And since the gap between the wall thickness is very thin, any centering issue can cause a drastic quality control issue in the model. And also, as you, the challenge here is to understand what is the interface between two polymers and avoiding the viscous encapsulation, and also the thickening, what I mentioned, thickening of the profile as it's coming out, thickening or thinning of the profile. So the factor what affects the co-extrusion with metal insert is the differences in viscosity of all the polymers that we are extruding. The die design itself, what die plates we are using and how the material is getting transition between two different ports and coming out of the die, and what process conditions we are using to extrude that polymer, and also the insert condition, like what speed we are pushing the insert and what is the temperature of insert if you are heating the insert also as it's getting into the profile. Click2Extrude helps in determining all these issues and understand upfront if there will be any issues in extruding this profile or not. So here I'm showing the one test case where two metal inserts are coming into this profile and two polymers are extruded, and one is U-shape and one is flat metal insert. So this was a real benchmark, and we compared with experimental data here, and this was the desired shape of the die, but because of the differences in viscosity and the speed, the blue polymer was pushing in and taking in shape of taking in area of the red region, as you can see here. Next, I'm going to talk about clamshelling. So when we are extruding for dies like coat hanger dies, where the polymer comes in from cylindrical area and that gets spread like a coat hanger, and there is a very high pressure at the center which pushes the die plates apart, and since there is a lack of bolting at the center of the die gap, that makes the expansion bigger, and that's what causes the clamshelling or expansion of the die. And clamshelling effect increases when we push the material with higher speed, and by pushing higher speed, that increases the pressure that is going to act on the die plate. So Click2Extrude helps in predicting if there is going to be clamshelling effect and how to optimize the process condition where we can minimize this effect. So here is one example. I'm showing how Click2Extrude is predicting the clamshelling effect. So here we can see the black line. What you see, that is the initial shape of the die, and it is getting expanded because of the pressure or push from the polymer that's coming through this. Next, I'm going to show a case study that we did before, and the goal was to optimize the die and reduce the clamshelling effect. So here the key variables in this analysis was the angle, as you see here, alpha, and how it is getting spreaded. So those two angles were the key parameters in this analysis. So using Click2Extrude, first we analyze how the polymer is flowing through the die and getting spread, and based on how it is flowing, what is the temperature rise during the flow, and how is the pressure drop from inlet till exit. So that pressure drop is very critical in designing a coat hanger die. So here we are plotting the thickness of sheet as it is coming out, and we are seeing the center one is thin because there is less flow there. And with Click2Extrude, we ran several test cases to understand the process window by changing. We can run with different process conditions. So here we ran with 7.5 to 22.5 feet per minute inlet speed, and then we analyze how the pressure drop is changing as the line speed is increased, and how is the pressure drop along the center line of the coat hanger die. And this is most critical to understand how is the pressure drop at end of the die, because that changes how the clamshelling is going to happen. And how is the temperature rise with all different line speeds. So based on all this analysis, we came to an optimized die where there was less variations in the extruded sheet, and also it was very well compared with the experimental data. In next few slides, I'm going to show a few applications where Click2Extrude is applicable and where we ran it before. So here I'm showing one spiral die that is used for extruding like a polythene bag. So here the polymer is coming in and it's going in helical shape and getting spread across the periphery and it's coming out. And here is one tube extrusion die similar to that. And next, I'm showing another application where it is applicable is in a runner balancing analysis for injection molding. So here it can be used to balance, optimize and balance the runner system for the injection molding. So the imbalance in injection molding runner is caused by the shear heating that happens near the wall, and that is with the very small degree of temperature variation, and that can cause the flow or the feed to each inlet to the part not go uniformly. So this causes the temperature to rise near the wall, and hence the hot resin will enter the part which is near the cavity, and the colder one will have less feed, as you are seeing in this part. So that's why the inner cavity will be hotter and they will fill quickly, and the outer cavity will fill slowly. So Click2Extrude can determine the flow imbalance, and we can determine which by making modification into runner system, we can optimize the runner system for injection molding. So here I'm showing how the polymer is flowing through the runner system and how the shear heating is happening near the wall, and as it is flowing through, where the colder and hotter material is flowing, and since this is little bit hotter compared to this region, so that's why we see more polymer getting filled on the top one compared to the bottom one. And this was compared with the experimental data. So the mass, we compared how much material is flowing through all these four exits for this injection runner system, and that was very well compared with experimental data. And the second phase of this benchmark was to make modification into runner system and come up with a new design to avoid this problem. So as part of that, it was the melt flipper was invented, and the problem that we see here that was avoided by introducing the melt flipper in the runner system. Now I will go back to Click2Extrude and show the results what we just set up. So let me open up the result. So as soon as the results are ready, we can go to visualize the results and see how to understand the die behavior and where we can make the modification in the die to make the die better. So here, first and foremost, as I mentioned in my presentation, is to see how the part is coming out of the die. So here we can see the right hand section is coming out faster, and because of the way the feed is there before this land region, it is making the part to bend in downward direction. And also we can hide this die. We can also see many one would also like to understand, okay, how is the polymer coming out of the die exit, and this will make the understanding if where to make the changes into die. So if I'm looking at right after the die, what is the variation in the velocity? So here we can see there's a large variation, this right section which is very thick, and there is a very big pore which is feeding to this section, and that's why this is coming out faster. So the way to fix this one is reduce the feed section which is feeding this right hand side to make it a little bit slow, and also make the feed section of the middle portion of the die a little bit bigger so that more material can flow through that. And same goes to the left hand side. Here, this is not as prominent or as fast as the right hand side, so it could be like half of it. And we can also see, let me plot everything, and here we can see how the overall velocity as part is coming out. Next, we can also understand as the polymer is flowing through, we don't see inside the die how is the polymer is flowing through. We can also make the cut section and understand how the material is flowing through the die. So this will give more insight into the problem before we go and make some modifications into the die. So I can go and make, since the velocity here at the inlet is very small, so to see the variation, we can change the min max and see how the polymer is coming through. And let me go back and remove this section. Hide. So we don't have to remove the cut plane. We can just hide them and bring back again. Next is to see how the pressure is dropping as the polymer is flowing through the die. And based on what is the viscosity of the polymer and what is the temperature, we determine how what inlet pressure is required and how the pressure is going to drop as polymer is coming out. And it's very important to understand if the pressure drop is almost near to uniform or similar along the flow direction. If there is some variations like what we are seeing here, the pressure drop is not that smooth or dropping similar at each and every place, so we will see some variations in the polymer that is coming out of the die. That's what we are seeing here. So this will also make us understand where to make modifications in the die. Next is to see how the polymer is flowing through and how the so here what we are seeing is I'm pumping in the velocity the polymer at 300 degrees Fahrenheit, and based on the properties or the viscosity, the flow behavior, there will be shear heating happening near the die wall, and also shear heating happening between them. And because of that, the temperature will rise, and we will see at the exit how much there is a temperature rise. And we don't want the polymer to go super hot as it is coming out, because if it goes super hot, it may not hold its shape, and it will collapse when it is coming out of the die. So we want it to maintain the temperature and maintain its shape as it is coming out of the die. Okay, so that's what the temperature plot helps us. Next is residence time. Residence time is if you consider like any particle that's coming into the die, and it takes certain path to reach the exit. So residence times help us to understand at which region in the die which is flowing very slow, and how to rectify them. So here we can see that this region is coming out pretty slow. That is because of thin section, and here it is less. And we need to correct the die to have a uniform or near uniform residence time at the die exit, or else we'll have some issues in the polymer. Next, we can also see the strain rate, as the polymer is flowing, how is the strain rate is changing along the flow path. So this also makes this affects the quality of the part which is coming out of the die. So this helps us understand where the hot spots in the flow region, and if by adding some fit section to it can reduce the oscillations in the shear rate. And also we predict how is the viscosity is going to change through the flow path. Since there is a very thin profile, we can cut down and see how the viscosity is changing. Okay, so over and all, it shows the great insight into the extrusion process, which we cannot see with naked eyes as the polymer is flowing through the enclosed cavity in the die. Like where are the faster regions or the regions which are getting choked, and the regions which are getting hotter than what we intended, and by making some modifications into the die, how to correct those. So it will help in correcting the die and also the process condition by running the simulations with different material properties and running the simulations with different process conditions. Now I'll go back to my presentation. So in summary, Click2Extrude is a virtual press where it is used to identify and correct problems before making the first die. It is fast, easy and accurate and affordable. And in few mouse clicks, one can analyze the extrusion process. Unlike traditional die trials, Click2Extrude helps in achieving higher productivity at lower cost. Thank you. So if you have any questions, please feel free to ask.
Thanks, Narendra, for that great presentation. At this time, we don't have any questions, but if any of the attendees do have any questions or concerns, please feel free to email us at support@solidthinking.com. We'd be happy to answer those questions. Just as a reminder, the webinar was recorded and will be sent out via email tomorrow morning. It'll also be available on our website. Looks like a question just came in, and it states, is there a fitting tool available to get material parameters for viscoelastic material models out of experimental data?
We have fit material module in Click2Extrude, so that can help in fitting the raw data from lab where we have viscosity data at different temperature and different shear rate. Ravi, you want to add something?
Yeah. In addition, if you have the rotational geometry data, we can, from that data, we can determine the normal stresses, and using those normal stresses, we can identify the parameters for our material model for viscoelastic analysis.
Great. Looks like that's all we have for right now. Once again, thanks everybody for joining us today. Be sure to visit our website, solidthinking.com/Click2Extrude. Both the metal extrusion and the polymer extrusion webinars will be available tomorrow online, so please feel free to look at those again. And thanks for joining us. Have a good day.